continuation of section 1.3, we're going to talk about even and odd functions, and then we'll finish with the greatest integer function and kind of introducing that to you. You should be on page 9 of your packet. All right, even and odd functions. Let's first talk about the even function. An even function, they are symmetric with respect to the y-axis. Okay, and an odd function, they are symmetric about the, you need a, this is a typo here, about the origin. Here's how you determine if you have an even or an odd function. You are going to evaluate your function for negative x and see a function f is even if for each x in the domain, if f of negative x equals the original function, then it's considered to be even. And if it's even, then it's symmetric with the y-axis, such as this. The parabola is an example. Symmetric with the y-axis. If a function f is odd, then f of negative x is equal to the opposite of the function. So you substitute negative x in and you're going to get the opposite of the function. Here's an example of that. The cubic function. It is reflexive about the origin, so you can see there's some reflection if you just rotate that curve around the axis. Okay, so even and odd, the first thing that we're going to do is look at how do you determine by finding f of negative x. So that's our goal. We're going to do f of negative x, and then we just basically determine, is it even, is it odd, or neither. Let's put negative x in here. So negative x to the third minus negative x. You evaluate this, you get negative x to the third, then plus x. This equals, if you take a negative 1 out, which is showing opposite of, x to the third minus x. So you compare these two, you can see that this first one is the opposite of the original function. So in this case, this first example is considered to be odd. All right, let's look at example B. Again, you put in negative x and you evaluate that, or you simplify. So negative x to the third is negative x third minus 1. If you can try taking the negative 1 out to see if it is opposite or not. We can obviously tell it's not the same, but when you do that, you do not get the original function here. So this is neither. You either get the original function, you get the opposite of the original, or you don't get it at all. All right, putting negative x in. You can see here anytime that you have an even exponent, that's going to be a good indication that you might have an even expression or an even polynomial function. So 5 minus negative x squared is x squared. If you look at these two functions here, but because of that x on the outside, this whole thing is the opposite of. So this is odd. All right, putting in negative x for example D. So 7 minus negative x squared. This is equal to the square root of 7 minus, having a little problems with my pen today, x squared. They're exactly the same, so you put in negative x, you get the same function. This is considered to be even. All right, let's look at the last one. 2x to the 4/5. You remember a rational exponent, this rational exponent means the 5th root of x to the 4th. That's what it means. If I put negative x in, 2/5 root of negative x to the 4th, then we get 2 times the 5th root of x to the fourth. We can put it back into its form, 2 times x to the 4/5. And it's exactly the same. So this is even as well. All right, that's how you test even and odd. We're not really looking at this point in time at the graphs of them. We're just trying to determine yes or no. The next thing we're going to look at is the greatest integer function. The greatest integer function is, you want to skip over to page 10 here just temporarily, because we're going to come back to that example, that application problem. The greatest integer function, denoted by this symbol right here, and it's defined as the greatest integer less than or equal to x. It has an infinite number of breaks or steps, one at each integer value in its domain. And the basic characteristics we will look at, but let's talk about this. So here's what it's saying. If you put a number in here, the result of it is the integer that's less than it. It's the greatest. It can be confusing because it says greatest integer, but really we're looking at the integer that falls below it. The greatest integer that falls less than whatever you put in here. So for example, if I put in to my greatest integer negative 1.5, what is the integer that falls less than negative 1.5? The answer is negative 2. If I want to do what's the greatest integer of 6.1, what's the integer that falls less than 6.1? The answer is 6. That's what greatest integer is. Let's look at the graph. So I'm going to have my x and y axis here. All we do to do the graph is we build, you can build a table of values like this, and we can just substitute some values in. So y is my function. What happens if I put 0 in? What is the integer less than or equal to 0? You see, you can be equal to it, so it is 0. That's 0. All right. What about a half? What's the integer that's less than or equal to a half? The first integer less than or equal to a half. Answer is also 0. So you can see here my function is going to be from 0 all the way over, but as soon as I get to 1, if I put 1 in here, the integer less than or equal to 1 is 1. And that's going to bring me up to a different y value. It's my output. So it's open circle at 1, closed circle here, and you can see this is going to keep repeating all the way until I get to 2. So the result, anywhere between 1 and 2, the answer is 1, until you get to 2, and then it's 2. So this is just a step function that you're familiar with until you get to 3, and so on. So that's what the greatest integer function looks like. Let's do one that's below. So if I put in numbers all the way to negative 1, the answer between 0 to negative 1 is always negative 1 until you get past that. And there we go. That's what it looks like. A little stair step. Okay? All right, here are the characteristics. Your domain is from negative infinity to positive infinity. All x's can be put into there. Your range are just the set of integers like 0, 1, 2, 3. Your x-intercept and y-intercept. Let's go back to the graph. Here's your x-intercept right here. Anywhere between 0 up to 1, but not including it. Those are the x-intercepts. And then here's your only y-intercept, just at the origin. Okay? And then behavior. It's constant between each pair of consecutive integers, which means they're just little horizontal segments, and then it jumps vertically, which is going to give you your steps. Let's evaluate. Okay, so what is the integer less than or equal to negative 1? Answer is negative 1 because it can be equal to it. What's the integer less than or equal to 1/10? Answer is 0. Integer less than or equal to 1.5? Answer is 1. An integer less than or equal to negative 1.3 would be negative 2. And the integer less than or equal to 3.5 would be -4. There's a quick representation on how you can evaluate, and I know that these are not in your notes, not all of them, but you may be wanting to add a couple others with that. All right, last problem here is an application problem. It says the cost of sending an overnight package from New York to Atlanta is $9.80, and that's for a package weighing up to, but not including 1 pound, and then it's $2.50 for each additional pound or portion of a pound. So here's when it says portion of a pound, so I could ship something for 1.5 pounds, but I'm only paying for the first pound. I could ship something for 3 7/8 of a pound, but I'm going to pay the $9.80 and then 3 more pounds. Use the greatest integer function to create a model for the cost of the overnight function. So here's our cost. Cost equals, we already know it's going to cost $9.80 regardless of what the weight is. Okay, your weight has to be greater than 0, otherwise you're not shipping a pattern at all, or not a pattern, a box. All right, you're going to add to that $2.50, but here's where the greatest integer comes into play, times the greatest integer of x, and here's why. Because if you ship a package that's a 1/2 pound, the result of the greatest integer at half is 0. So 0 times 250, you're not adding to $9.80. If you ship a package at 1 pound, then the 250 times 1 will be the increase, and that's how it would increase for each additional pound. So here's our domain though, x has to be greater than 0. That is your function. Let's quickly sketch this graph. This graph will be not quite, it's just going to be kind of a representation. I'm going to do a break in the graph, and because we're going to start at 980, I'm going to start at 10 here. Start at 10, then I'm going to go to 12 and 14. All we want to just show you is how this is a step function. Okay, so 980, that's going to be anywhere from greater than 0 pounds all the way up to 1 pound, but not including it. So 980 would be here. Let's get rid of those original circles. I didn't mean to necessarily do those circles there. Okay, here's 1. So at 980, we have open circles at 1 and at 0. Now, if you add 250 to it, because now we're going to go after 1 pound up to 2 pounds, if you add 250, you're going to get 1230. So at 1230, 1 pound is going to cost that, and so does all the way up except for not at 2 pounds. You just keep doing this. So 1250 or 1230 plus 250, it's 1480, and that would be at your 3. So here we go, all the way up to 3. And so that's what that looks like. Now that concludes the greatest integer function in even and odd. Here is your assignment.